Let's continue our exploration of the ASA condition, but this time let's look at it in taxicab geometry. So I'm going to open this app that we have here, and I'm going to open it in the app like this. I'm actually going to look at angle, side angle, and angle side conditions together. So one of the things that we notice in taxicab geometry, we have the same result that we have in Euclidean geometry, that the sum of the measures of the interior angles of a triangle, it has to be pi radians or 180 degrees. Okay, so if you have the AAS condition, you can subtract the measures of the two angles you have from pi, or 180 degrees, find the measure of the other angle, and now you have the ASA condition. So AAS gives you ASA in taxicab and Euclidean geometry. But now the question is, does it make the triangles congruent? ASA, we found, did make the triangles congruent in Euclidean, spherical, and hyperbolic geometries. But what about taxicab? Remember how SAS worked for Euclidean, hyperbolic, and spherical, but not taxicab. We might suspect that taxicab is different here too. So here we have the same kind of construction that we did before. So let's look at it. Look at this. Start with a point. Start with the line segment. Okay. Next, at one end, draw an angle. That's this terminal ray. There's, of course, also the ray that goes through AB this way. And then draw the angle at the other side. Again, there's a ray going through BA to complete the angle. But where do they cross? Oh, just in one point. So there is exactly one triangle there. And we can measure the pieces. Okay. Oh, okay. Well, it looks like it's exactly like the situation that we had before, but not so fast. Look what happens now as I manipulate this. Here are the links over here. The links as taxicab links are changing. Now the angles are staying the same. Okay, you get all three angles to match up. And we're not worried that these things are changing as Euclidean things. We're just worried that they're changing as taxicab objects. So look what's happening is, as I move this point B around the taxicab circle here, we see that while the angles are all staying the same, the links of the sides are changing as taxicab links. Not the blue one, that because it's going around a circle, but the other sides are different. So in fact, there are actually infinitely many different congruence classes. For example, that one and that one have the ASA or AAS or AAAS conditions. They have four corresponding congruent parts, three angles and one side congruent, but they do not have the other two sides congruent. So there are actually infinitely many congruence classes here. Now you can break it in the same way that you can break the Euclidean situation. If these angles, these rays diverge from each other, then they will not touch. And when does that happen? That happens when the measures of these two angles is pi or bigger. If it's actually pi, exactly pi, there's a place in here where they'll be parallel. If these two add up to pi or 180 degrees, these will be parallel, not touch. And if it's even bigger, then they'll, just point away from each other in some ways and diverge. But if the angles are summed to less than pi, the two given angles measurements that you have, then you will have a triangle, but it could have all kinds of different classes. All of those will have the same angle measurements. They'll all have this same length for the one given side, but there are infinitely many different possibilities for the congruence classes as you go around. So once again, even though taxicab triangles look like Euclidean triangles, they are Euclidean triangles. When it comes to triangle congruence, taxicab is kind of in a spot by itself. It behaves very differently than the other three geometries.